So now we are moving forward to 2's complement and how to represent negative numbers in binary. Start with data representation. So imagine that you are the person who invented computer, and you are thinking about how can I represent negative numbers in computer. Just all the numbers are binary, just ones, zeros. And you can think about, what about we add one digit in the very front on the MSB as a MSB. So let the computer know the MSB will always be the sign bit, but not a real data. So probably we can use 1 as a minus sign because it's a bar, but just vertically, not horizontally, right? We just use 1 as a minus sign, but 0 as a positive, as plus. Okay, so that's what people did in the very beginning, right? But they found a lot of problems. That's why they didn't use it anymore. So probably when people invented the computer back to 1960s, 1950s, they were trying to use this kind of number system, use the MSB as a sign bit. But after they find a lot of problems, so in the modern devices, nobody are still using the MSB as a sign bit anymore. But now we still have examples and see why that's a problem. Data representation. You have unsigned and signed, two types of binary numbers. So for unsigned, this is what we just learned last week. So like the 01001, we just never care about the sign. So what is this? This will be 5, and this will be 5 as well, right? We just never care about the signs. So for the signed, we use MSB as a sign. So for example, so here, let's just write it down. For the signed version, so this is 5, and this is minus 5, because this digit is being used as a sign. So that's a minus sign, that's a plus sign. That's positive 5, that's minus 5. But there will be a problem. So what's the problem? How would you know? Yeah, the computer can recognize actually. So you just usually use a MSB as a sign bit. They are able to find that. So because every digit is controlled by a transistor, right? So it can always sense that. That's not a problem. But the problem is you are having, so what about this? You have two binary numbers, right? But what are they? Yeah, that's this, right? And that's this. So that's a problem. So that's why people don't want to use this anymore. Okay. And there's another one called one complement, another version is called complement. So the concept of the complement is, for example, I just give you some examples to in decimals. For example, 10's complement of 5 is what? 5. So 10's complement of 6 is 4. 10's complement of 1 is 9. That's just a concept, okay? So when people are saying that's 10's complement, so that's a name. It's not saying 10 itself, the complement to 10, not like that. It's just a name, 10's complement, right? So that's the name of that. So 10's complement of 5 is 5. 10's complement of 6 is 4. So for complement, in the beginning, people are saying, what about that? We have a binary number and we invert every digit, and that number will be the negative version of that number. What about that? Will that work? So this is called 1's complement. The reason is, if you have 0101, so what's a 1's complement of that number? You just use 1, 1, 1, 1. So 1 at every single binary digit. Subtract the original number as that digit for that number. So for 1's complement of this guy will be 1, 1, 1, 1 minus 0, 1, 0, 1. So just 1's complement to every digit is 1, 0, 1, 0, right? Yeah. I think probably 40 years ago or something, people are still using, some of the systems are still using 1's complement to do some of the work. So 1, 0, 1, 0, that will be the minus version of that number. For example, this is 5. So let's use this number as minus 5. You know, you just let the computer, you just make a lookup table in the computer. Just let the computer know, hey, this is a positive number. These are all the negative numbers. So now here's a problem. So what if, so what about this? 0, 0, 0, 0, and 1's complement is 1, 1, 1, 1, right? So you have two binary numbers. You have two different binary numbers are actually representing the same number. And what is that? That's 0, and that's something is minus 0 or something, right? But they are the same number, but you have two binary numbers. Sometimes can cause some problems. So that's why finally people start trying to use 2's complement, which are being used in every digital device like your laptop, smartphone, and computers. They are all 2's complement. And we can verify pretty soon using a calculator. So what is 2's complement? So let's start with the concept. So concept. For definition. So this is how you get the definition of 2's complement, but in a real life, I never use that for calculation. But you need to know where does that come from. So 2's complement, for example, we have 0, 1, 0, 1. We know this is plus 5. It's also plus 5 in 2's complement, no problem. So what's minus 5 in 2's complement? We actually use 1, 1, 1, 1 minus 0, 1, 0, 1. That's the first step, right? That's the first step to get the 1's complement first, which is 1, 0, 1, 0. And then we plus 1 to that number, which is 1, 0, 1, 0 plus 1, which is 1, 0, 1, 1. And that number is called 2's complement. Of that number. And we define this number is minus 5. Have we ever learned this before? No. Okay. So that's by definition. If you convert a positive number to a negative number in this way, you'll never get a problem. So invert it, invert every digit, invert and plus 1. Remember in this way, invert and plus 1, invert plus 1, invert plus 1 will be the 2's complement. So let me know 1011, what is that number? You don't know? So what about this? In 2's complement. So right now we are talking about everything to 2's complement. So what is this number in 2's complement? So for the positive numbers, it's not changing at all. It's the same concept that it's 1011. It's still 1011 in the unsigned binary number, as we learned last week. But we put a 0 in the front, so which means it's a positive number. It's a positive 2's complement number. So what is that number? So what is this? 8. What is this? 2. What is this? What is this number? Positive 11. So what's minus 11 in 2's complement? What's minus 11 in 2's complement? Remember here? You have a cheat sheet here. Just move your eyes. Just move. Invert and plus 1. That's it. Yeah, invert and plus 1. So invert it first. 1, 0, 1, 0, 0. Plus 1. 1, 0, 1, 0, 1. That's minus 11 in 2's complement. That's really hard. And there's a very easy way to do 2's complement in the future. I will tell you later. I invented. Not now, but just introduce a definition for here. Seems like it's really hard. I have to invert and plus 1. So now I give you another number, 1, 0, 1, 1. You actually couldn't tell. Your brain could not resolve it. What is this number in 2's complement? You don't know. Do you know? You don't know. You have to convert it back. How to convert it back? Minus 1 invert, right? And then you'll see the positive number, and then you know what that minus number is. Can you get that? So minus 1, you got 1, 0, 1, 0, and invert it. 0, 1, 0, 1. So what is that? 5. So what is this number? Minus 5. So keep in mind, your brain, at least my brain, cannot resolve this number without any calculation. I don't know. I don't know what is that. But I will let you know one technique can get that number really quick later. But now you couldn't tell, right? Can you tell? If I give you, for example, 1, 0, 1, 1, 1, can you tell what is that? You cannot. You cannot. You have to convert it back. How can I convert it back? I'm repeating. So how can I convert it back? Minus 1 invert. So see the positive number, and you know what's the absolute value of that number. Just add a minus sign in the front. You know it's going to be the minus that one, right? And how can I convert a positive number into a 2's complement? Invert and plus 1. How can I convert it back? Minus 1 invert. Do you get that? Okay. Think about it one more time. Give you more examples. All right, yeah.
You know that you're working in this 2's complement space and you need to apply these additions and inversions?
Yeah, I will let you know in the problems.
Okay, so it's not something you can look at the number and
no,
whether you read it or...
No, it's by definition, totally by definition. It's not actually, so for this one, definitely, if it's a binary number, it is not minus, I don't know what is that. So for example, this one, it's not minus 5 at all. Is it minus 5? It is not. What is this? It's 11. In unsigned binary numbers, like as what we learned in the first week, it is 11. It's not minus 5, because we don't have any other way to represent negative number in the computer. So we have to, assign part of the numbers into probably 50% of the numbers into, just assign them to let people know these are negative numbers. It's all by definition. So we did that. It's not defined by the God. It's totally not. It is not minus 5. Right? It's not. We just define, we force this one to be minus 5. So now here's a way to calculate. You agree with that, right? You couldn't tell what is this number is. You have to do what? Minus 1 invert. All right, repeat. So I'm going to let you know one way to find out what is that number is. 10111, still this number. Okay. So all the rest of the numbers, except for the MSB, all the rest of them, you just think about these values are positive values. So what is it? Just don't look at this. If I give you a number in 2's complement, don't look at this. What is this number? 7. However, in 2's complement, you treat the MSB as a minus value, as a negative value. But you still use the absolute value as that digit. What is this value here? Absolute value. 16. However, it's not 16 to its complement. It's minus 16. Why? So that's the way you can know what is this 2's complement is super quickly. That's a magic in there. That's a secret. Right? Remember that. So whenever you see a 2's complement number like that, this applies not only to someone have an MSB to be 1, but also MSB to be 0. It's the same concept. 0 minus, and then add them together. That's a real 2's complement number. What is this? Minus 16 plus 7. What is that? Minus 9. Can we verify that in 2's complement definition? How to verify that? One more time. Minus 1 invert. So minus 1, 1, 0, 1, 1, 0, right? Invert 0, 1, 0, 0, 1. Is that 9? Is that magic? You don't need to do this anymore in the future. Is that easy? 1, 1, 1, 1, 1. What is that? It's minus 1. No, let's start. Don't start from there. Let's start from. What is this? So what is this number? It used to be 2, right? It used to be 2, but in 2's complement, it's not 2. What is that? Minus 2. What is this? It's still 1. So what's this number in 2's complement? Minus 1. What about this? What this number used to be? It
used to be 4.
But right now, minus 4. What is this? What is this? What's the final result? What is this?
-1.
Wait, what is it? Yeah, I know, but what is this?
-8.
What are they?
7.
What is that? And why?
-1.
And why is that? In 2's complement, why is that? Intuitively, still, why?
Everything's going to go to 0 except for the last digit, and then you just have a negative up front.
Yeah, that's from a definition, but intuitively, why is that? So this number is all the other numbers plus 1. And that guy is minus. That's why. All the rest of them add together, you get a number has an absolute value which is 1 less than this digit. You agree with that? Because all these numbers plus 1, you get a carry, which is this guy. But this guy is minus. So you got a minus 1, always. Right? What's this? Wait, come on. In 2's complement. What is this?
-2.
So what is this? What is this?
-2.
What is this? Why is that?
Based on the same principles that you just talked about.
Yeah, so same concept, right? So this number and this number, so what's the difference, absolute value difference? 2. It's always minus 2. So we got a conclusion here. So whenever you're adding ones in the front, for 2's complement, you are not changing the value. You can add a million ones in the front. It's not changing the value. And now let's verify. Since we know the laptop is using a 2's complement system, see if that's right. And we are verifying our consumption, our hypothesis from a real device in the real world right now. So we convert it to programmer. See all this. I'm sure you can do it here, but I'm not letting you know that you can do the homework in this way. Okay? When you're converting numbers, you need to show the process to get a credit. If you directly put a number in there, you got 0. Is that clear? Okay. So, what you want to use? So for some binary, okay? I put a 1, 1, 1, 1, 1, 1, 1. No. Let me see. How can I do it? Let's do it in decimal. So if I do a calculation, and you can see what the binary number here will be. So if we do, so we want to, for example, we want to get a -1 as a result. So let's use 5 minus 6 equals to. Did you see anything? You didn't see what I'm doing? Did you see what I'm doing? What does bin mean? It's not mean a trash box, trash bin or something. It's binary, right? So how many ones you have here? You think, don't count, just think about it. Wait, is that 64? Why 64? That's a 64-bit operating system, right? So every single digit represents one binary memory in the computer. And how many ones you have? 64 ones. And is that -1? It is -1. So that's, you see -1 in the decimal version, and in the binary version, it's going to be this. It's just super little number, but you see how many ones, how many transistors are being turned on in there. Just on. Right, 64, a lot of power. So let's try another one. 5 minus 7. Let me know the answer in binary. 5 minus 7. What's the answer in binary? 1 0. Where's the 0? LSD, right? Yeah. See? And at least we know this laptop is in 2's complement, not 1's complement, right? It's a 2's complement computer.
What would still run on 1's complement?
I don't think so. I don't think anything is still running on that. It's everything, even our final project is running on 2's complement. So yeah, I think everything is 2's complement. Some examples. What is this in 2's complement? Why is that? Because, you add everything here to a number which is should be a positive number, and this one should be a negative number, right? And if you have this number, you want to add 1, that will be 1, 1, 1, 1, 1, 1. If you add 2, it's going to be 1, 0, 0, 0, 0, 0, 0, right? So the difference between this number and this number, on the absolute value, the difference is 2. So that's why this one is actually minus 2. So this will be yeah. If I give you a 2's complement, a binary number in 2's complement, for example, this. So in the beginning, when we are doing the, so by definition, the 2's complement is, by definition, remember that? It is invert and plus 1. So you can get the 2's complement, the negative number from there. If you convert it back, what you are doing is you minus 1 and invert. So when we are doing the traditional way, and we want to figure out what is this number is in what's a positive number for this number, what would you do for this? Minus 1 and invert every digit, right? So it's going to be 1, 1, 0, 0, minus 1, and then invert. So we know this number is minus 3. Yeah, here's one quick note. If I give a number like this, can you tell me in a second if this one is negative or positive? And why? Just in 1 second. Negative, and why? Yeah, because this MSB is 1, because this one has a bigger absolute value and it's negative. So the absolute value of this single one is bigger than all the rest of the digits add together, right? So these are positive and this is negative, so that's why the final result should be negative. If I have a number like 0, 1, 1, 1, 1, 1, 1, 1, 1, can you tell me in a second if this is negative or positive? Positive, because there's no negative number at all, even, right? So can we get a conclusion that we only need to look at the MSBs and we know if this 2's complement binary number is a positive number or negative number? We can't, right? So if you have a 1 in the front, then we know it's a negative number. If there's a 0 in the front, it's a positive number, right? So we just do a calculation in the traditional way and we just verify that. But if we do it in a quicker way, remember that this number is, in 2's complement, this one is minus 8, and all the rest of them are 5. So you can directly add it together and get minus 3. So in the future, if you use this way to do that, 2's complement calculation, you can directly get the number by just doing some simple calculation. You don't need to convert it back, minus 1 and invert every digit, right? You can directly just do this kind of addition. Use a minus of this number plus all the rest of other digits. Okay. Just do a quick review on 2's complement. Any questions on this so far?
2's complement was invert and then plus 1?
Yes, to get a negative number. If you want to convert it back, you are doing inversely. So 0. So you want to get the 2's complement, get a negative number of this one, or get the 2's complement of this number. You are doing invert and then plus 1. So you are doing invert and plus 1. The purpose is to get the negative number of this number. Okay. So what is that? 1, 0, 1, 0. That's invert. Plus 1. Okay. So what is this number? This one? 5, right? Plus 5. And this one should be negative 5. Because the entire purpose of using 2's complement is we are trying to introduce negative numbers in binary. Right? So that's the purpose. We already know all these positive binary numbers easily. We covered that in the first week So all these binary arithmetic. So all these things are simple, but when you are trying to introduce negative numbers to binary, you were, introduce the y we are not using directly, just add a 1 sign bit in the front as MSB, because we got a problem for the zeros. And we're not using 1's complement as well, because we got a problem of zeros as well. So finally, 2's complement can get rid of that problem. And why?
So when there's a 1 in front, you do it backwards.
Yes, if you have a 1 in front, you already know that it's a negative number. This is a conclusion we just got, right? Just now.
Minus 1 and then invert?
Yep. To convert it back to the positive number, right? If you see a number with MSB which is 0, which means it's a positive number, and you cannot convert it to a positive number anymore, right? So you just want to convert it to a negative number, which will be invert and plus 1. Okay, so that's from, I will do it here. This is actually a pretty good question. So in 2's positive to negative, you are doing invert and plus 1. Okay. Negative to positive, we are doing minus 1 and invert. Okay, clear? So now let's draw the classic chart here. So if we start, for example, we have a 4-bit binary number, and we start counting. 0, 0, 0, 0 will be 0, no problem. 0, 0, 0, 1 is 1. 0, 0, 1, 0 is 2. 0, 0, 1, 1 is 3. 0, 1, 0, 0 is 4. 0, 1, 0, 1, 5. 0, 1, 1, 0, 6. 4 plus 2 is 6. 0, 1, 1, 1 is 7. So that is 0. That is 1. That is 2. That is 7. So what's next?
8.
So next will be 1, 0, 0, 0, right? Yeah, this one plus 1, we start counting from 0 to here right now. So this one is what? Minus 8. So see, if you have a 4-digit, 4-bit binary number, the maximum positive number will be 7. You have to keep the MSB to be 0 and keep all the rest of the digits to be 1s, right? This is how you can get the maximum positive number. So it's going to be 7. Because the next one won't be 7 anymore, won't be positive anymore, will be negative. And what is this? Minus 8. And which is a maximum, which is the smallest negative number for 4-digit binary in 2's complement? Is this the minimum one? Which one is smaller? Whenever you add more digits there, they are going to be positive. You're adding to it, right? So that's why this is the most negative number in a 4-digit binary 2's complement number system. So what's next? For counting up, this is most negative.
Least negative.
Because the MSB is negative.
Yeah, but then if you added 1, wouldn't -9 be more negative?
That won't be -9. You add a 1, it's a plus 1. So it's going to be minus 8 plus 1 will be minus 7. So 1, 0, 0, 1, right? That's next. Yeah, it's going to bring it back to 0. It is. So it's a circle. That's why I drew in a circle. That's minus 7, right? And next, 1, 0, 1, 0 will be minus 6. I just keep going. 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0. Huh? Oh, sorry. Okay, thanks. Is that right? 1 plus 1 plus 1. This. They're all right. We have the next one, 1, 1, 1, 1. You let me know what are they. What is this? Couldn't hide anything. Minus 5, minus 4. Why is minus 4? Negative a plus 4. What is this? Negative a plus 4 plus 1. Is that familiar? Like I just give you an example on the first page in the beginning, right? So when you have something like that, doesn't matter how many ones in the front, it's going to be minus 2 always. And verified. What is this? Yeah, always. If you have a million of ones, it is still minus 1. But it's a 1 million bit computer system. What's next? That's it. If you plus 1 to this guy, what's that one will be? 0. And you have one more bit as a carry in the front. However, this is a 4-bit computer system, so every memory bank has 4 bits in there. When you have this guy, we know it's we call it overflow, so we are not counting that, so it's coming back to 0. So you only have 0, 0, 0, 0 for 4 bits as 0 in the computer system. Do we have another 0? Doesn't like one's complement and the other one have a sign bit in the front, right? So 0, 0, 0, 0 will be the 0 forever. You don't have another binary number to represent 0 at the same time. So that's why 2's complement is great. There's no problem of that same thing. So here's a conclusion. If you have a 4-bit binary number, then what's a number range you can represent? Use a 4-bit binary number in 2's complement. What's the range? Yeah, so if we write it down in this way, it's going to be 2. That will be, wait, is that right? Because this one, so for example, we have 4 bits. So n is the number of bits. So we have 4 here. So 4 minus 1 is 3. And that's 8 here. 8 minus 1 is 7. It actually should be like that. Right? So smaller than 7, but bigger than minus 8. So you'll know that if we have a 10-bit binary number in 2's complement, what's the range? So you can use this conclusion for that, right? So now you understand that why do we use 2's complement and how we can represent negative numbers in binary without using a sum bit in the front. How? We actually just divided the entire number range into 2 halves. So 1 half here, since the 4-bit binary number, we can have totally 16 numbers, right? From 0 to 15, so 16 numbers. So 16 numbers, and we use 1 to 7, or you can say 0 to 7 as, but 0 is 0. So 1 to 7, they are positive numbers, and minus 1 to minus 8, they are negative numbers. So we just divided the entire number range to 2 halves. So this half is being used for negative numbers, and this half is being used for positive numbers. That's a strategy, and there's the only way we can do. I mean, if our more talent, you can think about another way to do that, but I don't know. This is the current computer is based on this 2's complement number system. Anything left? Oh, overflow, important concept. Overflow. So the definition of overflow is if you have a positive number plus a positive number, but final result is a negative number, then you got overflow. If you have a negative number plus a negative number and finally you got a positive number, you got overflow. But for the rest of the cases, you are not getting overflow. Pretty important concept. You are going to use this for the IPGA programming in the future. So we are going to design a little ALU on the IPGA, and you have to understand this in order to program the IPGA. If you have P plus N, you got a P or N, it's not overflow. If you have a, yeah, that's all the cases we can cover. Why is that? So we are all talking about in 4 bits or in a certain amount of bits in the computer system. If you have a number like, example, minus 25 plus 7, that's P plus N. Oh, no, that's N, that's negative plus positive. So by the definition, you will never get overflow. That's just definition, right? This is just introducing you the definition right now. You don't need to, oh, so what is overflow? What is, so here's overflow. If you have these 2 cases, it's gonna, we are calling that overflow case in the operation. And you'll see how that works later. But now let's just remember the definition right now, okay? If you have a positive number, add a positive number, you get a negative number in 2's complement, then it's called overflow. If you have a negative number plus a negative number, you get a positive number, you get overflow. So intuitively, what that looks like. So if you have a positive number in 2's complement, what that looks like? Don't think about anything else. What's a necessary condition you need to know if that's a positive number in 2's complement? I must be 0, right? So it's going to be 0 something plus 0 something, and you got a 1 something, but always 4 bits, always in 4 bits, always in 4 bits, because the computer has, if it's a 4-bit computer system, it's going to be always 4-bit computer system. You cannot change it. Is that possible? I mean, in real life, you have $5, you receive another $5, and the result is negative $10. Sounds really bad. So that's a problem with 2's complement. And it's going to happen sometimes. And why it's going to happen? Why it's going to happen? Yeah, you need a 1 more bit in the front, right? So all the memory banks are 4-bit. That's a memory bank. So every row in the memory bank is a 4-bit number system. And you have this guy, which is A and B, A plus B. And you finally get a 4-bit result. So A has MSB to be 0, B has MSB to be 0, but A plus B equals to C. And in the result of C, you got a 1 in the front in MSB, which is not right. You don't want to just use a 4-bit, the 4 bits to represent as a result for this addition, to let the computer know, hey, this 4-bit is the result. It's not. You need to borrow another memory bank. So you are telling the computer, so there will be a overflow indicator in the future you can design. It's a digital logic block. You can use a transistor to design the blocks and indicate I have an overflow. We'll introduce this later in the final project. Just to let you know, it's given that you will have an indicator. So whenever you have overflow, the computer will know, I have an overflow right now. Then what's the next step for the computer to do? If you have overflow, so the computer should adopt this final result or not? No, because it's not right. And I know there's an indicator already telling me there's overflow. So which is actually telling me do not just use the 4 bits as a result, because that's not right. So which is right? Use another memory bank, since you need just combine them together. So this 4 bit is not 4 bits are not enough to give you the result. So you need another 4 bit in the front to combine them together, so the computer can do that work. Don't worry about that. So now you need something else. They're all zeros, and combine them together. So the final result will be 0, 0, 0, 0, 1, something, 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 something here. I don't know what are they. But at least I have 4 zeros in the front, will indicate this number is positive, right? So 4 bits are not enough. I need 8 bits. Why not 6 bits? Yeah, you don't have 6 bits. I mean, just take another 4 bits. Just take it for free. Keep the changes. So total 8 bits. Right? So 8 bits, and you have the 3 bits in the front as, actually you only need 5 bits because you only need 1 more in the front, right? But you have extra 3 bits. They are not changing the value. These are just zeros in the front, not changing the value of the binary number. We'll give you examples on this later. It's just giving you some intuitive, concept about how that works. So this one, what's the result? What's the final result for this calculation? In decimal. 18? Yeah. Minus 18. So this is negative plus positive, and you got a negative. Cannot satisfy any of these two conditions. So no overflow. No overflow at all. Why no overflow? Intuitively. I always want you guys to think about everything intuitively so you can understand that forever. Doesn't like you memorize a method and you don't understand it. You just do it on the paper like a robot and you'll forget it in a second, right? So now why? Why is that? Why no overflow? Yes, intuitively. So I have, yes, good catch. Let me explain this more on that. So you have minus 25 or right A. So for example, how many bits I need for minus 25? Probably, let's see. So I need a minus 32 first, and I need a 32 plus what? 7, right? 32 plus not 16, not 8, but 4 and 3. Is that minus 25? So this is minus 32 plus 7. Yeah, minus 25. So now let's assume that we are using a 6-bit computer system right now. And I need a 6-bit for 7 as well. So it's going to be 0, 0, 0, 1, 1, 1. Okay? So I already have 6 bits to represent minus 25. And I'm adding, so I know this is a negative number. And I'm adding a positive number to a negative number, which means I'm reducing the absolute value or magnitude, right? I already have 6-bit, which is enough to represent minus 25, this magnitude, and I'm reducing the magnitude. Do I need more bits or not? No, 6-bit is good enough. So that's why when you have a p plus n or n plus p, you are reducing the magnitude. You don't need more bits for that, since you already have that many bits, which is even more in addition, in the operation. You get that, you get that, You probably watch the video later if you cannot. Intuitively understand this will solve the problem forever. Why is that? Why P plus N or N plus P will never get overflow? Because you are reducing the magnitude or the absolute value.
So it's smaller.
Smaller, so the absolute value will be smaller.
Than whatever the biggest number was.
Yes. Make sense? Kind of. Yeah. And why overflow can only happen when you have P plus P or N plus N? Because you are increasing the magnitude, there's a chance. But will that happen 100%? No. 0, 0, 0, 1 plus 0, 0, 0, 1. P plus P is 0, 0, 1, 0. Still positive. Satisfy any of these two conditions? Wait, come on. Does this one satisfy any of these two conditions? P plus P is P. So what are the only two conditions for overflow? PP, you got an N, N, you got a P. So which means it's wrong. PP, how can I get an N? It's wrong. N, how can I get a P? It's wrong. PP and P, this is right. PP, you can get a P.
Just to clarify the overflow definition, that's like referring to an error that occurs because of it, not just when a one transfers over. Because when I was doing some of the addition, you end up with a whole bunch of ones and one kind of overflows, but it doesn't actually change the number.
I think that's different. So overflow here means it's in 2's complement, but what you are saying probably is in right.
Yeah, I was working in 2's complement and I would just have a one carry
yeah.
to another place, but it wouldn't actually change the number. Is that considered overflow or is that just? Because it doesn't give an error.
Is that in 2's complement?
It is a 2's complement.
And if that falls into these two cases?
No, I get a positive plus a positive is equal to a positive. Or a negative equal to negative. So it works fine, but I just have that carry.
Yeah, then you don't want that carry.
And I don't want it, I don't care about it.
Just toss it, yeah. If you include that carry, then you get a wrong number, wrong result, right?
And so getting rid of that carry, that's not considered overflow?
Yes, so that's why you need an overflow indicator to telling you if you want to adopt that carry. Right.
From -1 to 0, you have overflow.
Say it again, that's right.
So for like -1 and then you add 1. Oh, okay. Because it's positive. But wait, you still have overflow, you said.
Which one?
When you go from -1 to 0.
From
the previous page, we got 2 lists. On the left column.
So -1 is this one, 1, 1, 1, 1, right? And +1. Good question. So what's this number? What's this? No, N, right? What is this? P. Is there a chance to get overflow? No, N plus P. Remember, you are reducing the magnitude. However, you get a carry. That's a good example. So you are getting 0, 0, 0. You get a carry. Do you have overflow? So carry, but no overflow. So do not use this number in the result. Why? Because no overflow. No overflow means you don't need one more bit to represent the result. 4 bit is enough since you are reducing the magnitude. So do not adopt one more bit. We'll change the number. 4 bit plus 4 bit. One of them is negative. How can you get the result which is 5 bits? It's impossible.
How would you recognize that?
Because it's N plus P. Remember, overflow only happens here. So which means, let me write it down on the paper. Yeah, let's do it here. Something you want to put your notes. So overflow Then do what? Adopt the, it's not a carry, it can be 0. So I don't want to say carry, adopt a carry. No, I don't want to say that. Adopt the from bit, or adopt the bit in the front. How do I want to say that? I hate my English teacher. Adopt one more bit in the front, right? No overflow. Just don't do that.
So it's no overflow and there's a number on the end, just.
Yeah, don't use it, yeah. So that's why you need an overflow indicator. So you can design the logic system to detect if you have overflow. How to detect that? Interesting, right? In the future, we'll introduce how to design a circuit to detect, hey, I got these 2 cases and I got overflow. I'm going to adopt the front bit. You have signal, right? You have signal, so you have a chance to detect that. If you don't have signal, then how can I tell if I have overflow? You cannot tell. But you can tell here because you have this definition, right? You will know how to do it later. Don't worry about that. Yeah, some examples I want to show you. So you can let me know if there's an overflow. 5 plus 6. So you need to let me know what's the result and if there's an overflow happens. It's 11, right? That's a result. Do you have overflow? So 5 is 101, is that right? Yeah,
0.
that's 5.
It depends on whether you do 0, 1, 0, 1, or just 101 for the reveal.
No, 101 is not 5. 101 is minus 3, right? 2's complement. So 5 has to be 0, 1, 0, 1, 0, 1. What is 6? 0, 1, 1, 0. What's the result? You have P, you have P. There's a chance to have an overflow. It can be 1, 1. Uh-oh. What's happening? P plus P, I got an N. It's not right. So that's why the English here is hard to describe it. To adopt the MSB, what is MSB? This guy, to adopt it. I already have it here, why? Right, so adopt one more bit in the front. What is one more bit? As long as it's not changing the number, changing the value. Well, it's changing the value. If you don't have a, so PP, you got an N, which is not right. You need an N, you need a P, right? So in the P means you need this. So for the result, you need to add a 0 in the front. That's it. That's everything you need to know. The computer needs to do. You get a correct answer. Second example.
Are we going to do everything? Choose call?
I think after this lecture, we are going to move forward with Boolean algebra and then transistors, then circuit simulations and logic gates, then logic blocks. There's nothing about numbers. And then the last 2 weeks will be a project, and we're going to use this to build a computer on the FPGA. Yeah. But after this lecture, all the rest of the semester before the project will be unsigned binary numbers, just logic, voltages. You have circuit 1 as a background, circuit 1, and you're doing circuit 2, you hate it. Or do you have circuit 1? You all have circuit 1? You all have, right? Great.
Yeah. Okay.
And networks 1? -5 plus -6, which is -11. Right. What is -5? -5 is -8 plus 3. -8 plus 3 plus -6 is -8 plus 2. Right? What's the result? You got n, 1, 0, 1, 0. Oops. Right? Do you have overflow? Yes, you do. Do you have overflow here? In the previous one. So you know you have overflow. So what's the action you want to take? Adopt this one. If you do not have overflow, you got to carry. Do not adopt that. You have overflow, so adopt that. More examples? I don't have more examples.
Could you do one of carry where you drop it?
Okay. So make up example. That's easy. Let's just still use that for -1 plus 2. That's 1, right? So what is -1? Yeah, what is 2? What is 2 in 2's complement?
0, 1, 0.
What is -1? If you have a 3-bit, you have 3-bit here as well, right? Just keep it consistent. So 1, 1, 1 plus 0, 1, 0, you're getting 1, 0, 0. So which is n plus p, you got a p. Do you have overflow? Wait, n plus p equals to p, do you have overflow? You don't. Why? Intuitively. Yes, you're reducing the magnitude. So you don't have overflow, which means you do not need one more bit in the front. 3 bit is enough. So no overflow. Then do not use a carry. You do have a carry, but do not use it. So this just add a little bit computation load to the computer, but you can design a digital circuit to get rid of this easily. Do the calculation and indicate if overflow occurs. Okay, now let's see. So for the first one, it is 6-bit, right? So we just make a different definition. This is a 6-bit computer system, and we have 21 plus 11. So 21 is 16 plus 5. So 16 is like this, right? 1, 0, 0, 0, and plus 5. That's 5. And because it's 2's complement, so you'll need one more 0 in the front to represent 16. If you don't have this 0, it's going to be something else. And what is that? Minus what? Minus, if this is a 2's complement number, what is this number? What is this? Minus 16, yeah, negative 16. What is this? 5. So what's this entire thing? Negative 11, right? If you put a 0 in the front, it's 21, right? Keep in mind, this is a 6-bit computer system. So that is 21 in the 6-bit computer system. What is this number in 2's complement? It's still 21, but it's not in the 6-bit computer system. It's a 7-bit number. It's in the 7-bit computer system, okay? So that's one memory bank that has 7 bits in there. So what I'm saying, in the 6-bit computer system, you have to keep 6-bit. You have to have, so you need a 6-bit to make up this number, but not more, not less. Okay, if you need a 0, just make up 0 in the front. Finally, make it into 6-bit. So this is not right. So 6-bit 21 will be this. What is a 6-bit 11?
0, 1, 1.
So 11 is 8 plus 3, right? 3 is 1, 1. So that's a 4-bit unsigned binary number. And you want to make this to be a 6-bit 2's complement 11. You need a 2 more zeros in the front. Making sense? So now you have 11 plus 21, which is 0, 1, 0, 1, 0, 1. So that's 11 plus 21. Now we need to calculate this result in 2's complement and indicate if overflow occurs. Okay? Now let's add it up. 1 plus 1, you got 0, carry. And now 1, 1, which is 1, 0. 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. 6-bit. 6-bit plus 6-bit, we got a 6-bit. Is there a overflow? Yes. Why is that? It's P plus P, you got N. Why is N? Yes. So which means it's not right. So think about this is just the process when the computer does this calculation, right? It's the same process. You have an adder, which is a computer logic block. You have 2 addends as inputs go to the adder, and you add them up, and you get a result. Because the adder is a 6-bit adder, so the result is a 6-bit. And you want the computer to know if you want to use an extra bit in the front as a result, to be in the result. So definitely, if you have overflow, you have overflow indicator. You want the computer to know, like, this is not enough. There's overflow, so I need this to make the result correct. All right? So now, what about the same thing in a 7-bit computer system? So what is 11? What is 21 in 7-bit computer system? What that looks like? Yeah, 0, 0, 1, 0, 1, 0, 1, right? What about 11? 0, 0, 0, 1, 0, 1, 1. 8 plus 3. And you add them together. So you're getting 1 plus 1 is 0, 1, 0, 1, 0, 1, 0, 1, 0. Put 1 here, 0 here. So 7-bit. Add a 7-bit, and you get a 7-bit. Any overflow? No, because P, 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 right? So you're fine. Let's take one more example here. In a 5-bit Is everybody comfortable with this? This is going to be on the quiz, right? You're fine? Good? Okay. For example, which one you want me to go through? Which one? Before I pick up randomly. This one? Okay. 5-bit. How can you, wait, at least you know there's no overflow, right? Because it's n plus p is not in any of the categories, right? So no overflow at all. But what's the result? So in the 5-bit system, let's see what the minus 12 looks like. You need minus 16 plus 4. So here's minus 16 plus 4, right? Minus 16 plus 4. 5-bit. 5 bits, we're done. What about 13? 13, you need 8 plus 5. So 8 plus 5. And you need a 0 in the front to make a 13, right? And now let's add them together. 1 0 1 0 1 0 1 0. That's the result. That's n plus p, and you don't like that one, that carry, and you got a p. You know there's no overflow, right? So are you going to take this one as a result? No, it's no overflow, so you don't need that. That's kind of a defect in 2's complement, right? You got a carry, but you don't want to use it. All right. Any questions? Anything? Let's try one more. Minus 32 minus 1 in a 6-bit computer system. So minus 32 minus 1. Do you want to do subtraction? You want to do addition? Yes. So it is this plus this. Okay. And then what is minus 32? To be 1, 1, 2, 3, 4, 5. That's minus 32. What about minus 1? All ones.
Oh, yeah. 6-bit.
Looks weird, right? Minus 1 looks like way bigger than minus 32. Yeah. Just add them together, and you're going to get 1, 1, 1, 1, 1. And then carry and 0. So you have n plus n, you get a result which is p. So overflow or not? Overflow. So do you want to use this carry? Do you want to use this carry? Yes, use it. Because n plus n cannot be p, has to be n. So you need this one in the front. Right, that's it.